Howdy, welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture video for Section 1-2, Types of Data. Here you see a brief overview of what we're going to cover in this lecture. First, we're going to talk about the difference between parameters and statistics. Then we'll go into describing quantitative data, categorical data, and then finally in the lecture with an examination of levels of measurement. So let's dive in. So as was noted in the prior lecture, statistics essentially involves using sample data to make inferences about an entire population. We don't want to get data from every member of the population. What we want to do is get data from just a portion of the population, and that portion is what we call a sample. This is more effective from a time perspective, from a money perspective, and also from a manpower perspective. So that's how we're going to proceed. Go ahead and just get the sample and use the data from the sample to make an inference about a population. Now, sometimes those conclusions or inferences we make are going to be about the characteristics of a population or how the population is right now. Other times, the inferences or conclusions that we make are going to be predictions about the population. We're going to talk about what the population is going to be instead of what it is now. Either way, we can use statistics to get to those inferences and conclusions. But in order to do that effectively, we need to know and understand the definitions in this section. So let's go ahead and dive in. First, we need to understand the difference between a parameter and a statistic. A parameter is simply a numerical measurement describing some characteristic of a population. On the other hand, a statistic is a numerical measurement describing some characteristic of a sample. So parameters go with populations and statistics go with samples. Really important that you get this down because oftentimes the use of statistical methods requires us to distinguish between populations and samples. Are we talking about one or the other? So we need to understand the difference here. And part of the way we distinguish between populations and samples is with parameters and statistics. So parameters are used to describe populations. Statistics are used to describe samples. And the way I keep them straight in my head is I use alliteration. Notice that population and parameter both start with the letter P. So therefore, I know that those two are associated together. Likewise, sample and statistic both start with the letter S. So I know that statistics are going to use to describe samples. So I can tell whether or not something is a parameter or a statistic just by looking at, okay, am I looking at a population, in which case that's a parameter, or am I looking at a sample, in which case that's a statistic. Here's an activity that will help us to hone down this distinction between parameters and statistics. I'm going to give you some examples, and then you're going to tell me whether it's a parameter or a statistic. So, yeah, we're going to get right into the active learning right here at the get-go. So, pay attention. Here's your first example. In a traffic safety survey, 21% of respondents said they recently texted or emailed while driving. Is this a parameter or is this a statistic? I'll give you a few minutes to decide. Well, I hope you said statistic because that's the right answer. Okay, 21% of respondents is not the whole group. It's not the whole set. It's just a portion. Therefore, we're only going to look at a sample because that's a portion of the whole. And since we're talking about a sample, that means we must be talking about a statistic. Here's the next example. There are 50 state capitals in the United States. Is this a parameter or a statistic? I'll give you a few seconds. I hope you said parameter because that's the right answer. 50 state capitals is all there is, so that's the whole group. And since we're talking about the whole group, that means we have a population, and populations are described with parameters. Here's the next example. A study examined all 2,223 passengers aboard the RMS Titanic. Is this an example of a parameter or a statistic? I'll give you a moment. So here we're looking at another example of a parameter. All the passengers aboard the ship, that's everybody, so that's a population, and therefore we're looking at a parameter. Next example, the mean volume of brains in a neurological study is 1,126.0 cubic centimeters. Is this an example of a parameter or a statistic? I'll give you a moment. I hope you said statistic because that's what this is. Okay, don't look at what's actually being calculated. Okay, the value that you see here is a mean value, and mean is just statisticians' way of saying average. Don't look at what that is. The only thing you need to look at is, are we looking at a sample or are we looking at a population? And in this case, we're looking at a sample. We know this is a sample because we're talking about brains that are involved in a neurological study. No neurological study is going to study every brain that is in existence. We're only going to look at a portion of all the brains in existence. So we don't have the complete set. We have a portion of the complete set. That means we have a sample, and samples are described with statistics. Here's the next example. The mean atomic weight of all elements in the periodic table of elements is 134.355 AMU. Is this an example of a parameter or a statistic? I'll give you a moment. Well, I hope you said parameter because that's what it is. All the elements in the periodic table. So we've got all of them. We've got the whole group, the whole set. That's a population. And populations are described with parameters. Here's the last example we'll look at. In a random sample of households, 47% of households had HDTV. Is this an example of a parameter or a statistic? I'll give you a minute. Well, not a full minute, but you know what I mean. Okay, I hope you said sample. I mean, here it is. It's right here in front of you. It's, right here in the example sentence, in a random sample. Okay, sample. So there's your clue right there. We're talking about a sample. Even if it didn't say that, 47% is not the whole kit and caboodle. It's only a portion of everything. So therefore, we're talking about a sample. Sometimes you'll get examples that just say the word right outright. So you're looking at sample, you're looking at population, it says the word right? And that's just giving you, that's a freebie, man. You just take the freebie and you just take it and run with it. Okay? Just remember that statistics are used to describe samples, parameters are used to describe populations. Let's take a look now at quantitative data. Quantitative data consists of numbers representing counts or measurements. Now, oftentimes when you see data represented as a number, most of the time it will be quantitative data. That's not always the case. We'll get to that a little bit later on in the lecture. But usually when you see numbers as your data, it's going to be quantitative data because those numbers are going to represent counts or measurements. For this reason, quantitative data is also called numerical data, because the only way you're going to express counts or measurements is with a number. Here's some examples of quantitative data. The weights of supermodels, the ages of respondents, the number of eggs in a carton, the distance between two cities, the quantity of coins in a jar. These are all examples of quantitative data. Now, quantitative data, unlike ice cream, thank goodness, comes in two flavors. The first flavor is discrete data. The second flavor is continuous data. I'm a total fan of like vanilla, chocolate, but I'm so glad there's so many more flavors to ice cream than just two. But when it comes to quantitative data comes in only these two flavors. Let's take a look at each one of them in more detail. First, let's look at discrete data. You have discrete data when the only possible values are whole numbers. So you're counting things as whole units. That's discrete data. If we take a look at the examples of quantitative data we just saw, we can identify which of them are discrete data by applying the definition in each instance. First, let's look at the weights of supermodels. Well, the weight of anything is going to be described not just with a whole number, but with a part of a whole as well. So it's very, very uncommon for someone to be exactly a whole number of units of weight, whether you're talking about pounds, kilograms, what have you. So weights of supermodels would not be an example of discrete data. The ages of respondents, likewise, would not be an example of discrete data. Typically, when you ask someone how old they are, the response is given as a whole number of years, but that's not how old they really are. They really are a certain number of years, months, weeks, days. So you've got partial years as well as whole years, and therefore the ages of respondents would not be an example of discrete data. The number of eggs in a carton, well, now that is an example of discrete data because you only count whole eggs. When you're counting eggs, you don't count partial eggs, you count whole eggs. So this is an example of discrete data because the only possible values are whole numbers. The distance between two cities is, oh wow, I really skipped that, didn't I? Yeah, anyway, so the distance between two cities is just like weight or age. You're going to have a part as well as a whole, so that's not going to be something that we would call discrete data. However, the quantity of coins in a jar, yeah, we're not counting partial coins, people. We only count whole coins. So, therefore, the quantity of coins in a jar is an example of discrete data. Continuous data, on the other hand, is when your values consider parts as well as wholes. So it's not just a whole number. It could be a whole number, but it could also be something in between the whole numbers. That's where the name continuous comes from, because the possible values you have come from a continuous scale that covers a range of values. Let's look at the examples we just considered of quantitative data and see which of these are continuous data. The weights of supermodels. Well, now this is an example of continuous data because, as we just discussed, the weight of anything is going to be a part and a whole. So you're going to have a certain whole number of kilograms or a certain whole number of pounds, but then you're going to have a partial pound added in there with it. So the weight of supermodels, yeah, that's going to be continuous data. The ages of respondents, likewise, is going to be an example of continuous data because you have a certain number of years, but then there's a partial number of years, a part of a year that you tack onto it to describe the actual data point. So the age of respondents is going to be continuous data. Number of eggs in a carton, well, that's discrete data. You're counting only whole numbers. You don't count partials, so therefore you're not going to you're not going to say that the number of eggs in a carton is continuous data. The distance between two cities. This is an example of continuous data because you're going to use a portion as well as a whole unit to describe the distance. So it's not going to be a whole number of miles or a whole number of kilometers, but you're going to have a partial kilometer and a partial mile to tack there on the end to describe the full distance between two cities. And the quantity of coins in a jar, as we saw earlier, is an example of discrete data because you're not counting partial coins, you're only counting whole coins. So now that we've gone through and looked at the difference between discrete and continuous data, let's go through a little exercise to see if we understand the difference. And if we don't, then this exercise should help us to hone down and fill in our knowledge gaps. So the first example we have here is the measured chest deceleration during a crash test of a Honda Civic is 39 g. Is this an example of discrete data or continuous data? I'll give you a few seconds. Okay, this is an example of continuous data. I know it says 39g and 39 is a whole number, but it could just as easily have said 39.5 g. I mean, there's nothing that says it has to be a whole number. So this is an example of continuous data because we could describe it with a part as well as a whole. Here's the next example. Each Honda Civic has 4 cylinders. Is this an example of discrete or continuous data? Well, I hope you said discrete data because that's what this is. 4 cylinders, so you don't count partial cylinders. You're only counting the whole cylinder. And since whole numbers are the only values you have when you count cylinders, this is an example of discrete data. Here's the next example. The average number of words a randomly selected man spoke in one day is 13,825. Is this discrete or continuous data? Well, again, this is an example of discrete data. I hope that's what you said because that's what this is. You're not going to count a partial word, okay? Again, the average number, okay? That's what you're describing here. Don't look at what you're calculating. Look at what you actually have. So, we're looking at words. Words are counted. You either have a whole word or you're not going to count a partial word. So, because you're only counting whole words, this is an example of discrete data. The first earthquake from a sample had an intensity of 7.0 on the Richter scale. Is this discrete or continuous data? I'll give you a few seconds. Okay, this is an example of continuous data. Okay, the value that you could have could be a whole number, but it's not typically described as a whole number. 7.0 is the same as 7, which is a whole number, but this could be 7.1 or 7.2 or 7.3 or any value in between 7 and 8 or between 6 and 7. So this could be described as part as well as wholes. Therefore, you're looking at an example of continuous data. Here's the next example. The U.S. House of Representatives has 435 members. Discrete or continuous? I'll give you a few seconds. Here we have an example of discrete data. Okay, 435 members. You're counting people. And when you count people, you're only counting whole numbers. So because whole numbers are the only possible value, this is an example of discrete data. Here's the next example. The arm circumference of a randomly selected female is 27.5 centimeters. Is this discrete or continuous? I'll give you a few seconds. Okay, this is an example of continuous data. The arm circumference, okay, so you're basically measuring a length, and that type of measurement is the same as distance between two cities. That's just a length. So you could have whole units. Could you also have partial units included in the measurement? And so because you have parts and wholes, this is an example of continuous data. Here's the next example. George Washington was 188 centimeters tall. I'll give you a few seconds. Again, this is an example of continuous data. Any type of length measurement is going to be a continuous data because continuous data, remember, has parts as well as wholes. And so any length you could measure could have part as well as a whole. So therefore, this is an example of continuous data. Let's take a look now at categorical data. So in contrast to quantitative data, categorical data consists of names or labels which represent categories, hence the name categorical data. Categorical data goes by other names, so you may have heard this described as qualitative data or attribute data because the categories, which are represented in the names or the labels that comprise categorical data, are describing qualities or attributes about what the data is describing. Here's some examples for us to look at for categorical data. The gender of professional athletes. Okay, it's a category. It's not necessarily a number. It's not numerical. There's no quantity involved. It's a quality. So we're looking at simply a name or a label. This makes it categorical data. The alma mater of respondents. So whatever school you went to, that's going to be categorical data. The type of milk. Okay, notice that we have numbers here. Fat-free, 1%, 2%, and whole. Certainly, it's easy to look at, say, fat-free and whole and say, well, that's obviously categorical data. But 1% and 2%? Well, even though the 1% and 2% represent measurements, here in this case, it's actually used as a name or a label. And that's what makes it categorical data. So even though it's a number, it's really not numerical data or quantitative data. It's what we call categorical data because it's describing a category. It's a name or a label. Likewise, the shirt numbers on professional athlete uniforms. Okay, the numbers are just substituting for names. And so because it's a name or an identifier, that makes it categorical data. So even though they're numbers, don't just say that because something is a number that it's automatically quantitative data. That's not always the case. Sometimes numbers can be categorical data. So you need to look and see, is this a name or a label for something? Is this a unique identifier? If it's a unique identifier in some way, then that's going to make it categorical data, even though it's a number. Let's talk a moment now about levels of measurement. Levels of measurement is simply another way to classify data. There are 4 types of levels of measurement. First, we have nominal. Second, we have ordinal. Third, we have interval. And fourth, we have ratio. Let's take a look at each one of these 4 types so we can understand the differences better. First, we have nominal data. Nominal data has 2 defining characteristics. The first is that it consists of names, labels, or categories only. That means nominal data, the nominal level of measurement, is going to consist of categorical data. If the data is quantitative, then it's not going to be nominal. In order to have nominal level of measurement, you've got to have categorical data. The second characteristic is that it cannot be arranged in any sort of ordering scheme. Here's a good example. A survey with possible responses being agree, disagree, or not sure. So agree, disagree, and not sure are certainly names, labels, or categories, but there's no real, obvious order to how you would say this. So you could order it as not sure, disagree, agree, or you could say agree, disagree, not sure, or you could say disagree, not sure, agree, or agree, not sure, disagree. There's different ways that you could try the order, and no one of them is any better than any of the others. No one of them seems more natural than any of the others. So there's no real way to order this. So that makes this nominal data. Ordinal data also has 2 defining characteristics. So the first is that it can be arranged in some order. So in this way, ordinal data is different from nominal data. However, the differences between data values either cannot be determined or are meaningless. Here's a good example of ordinal data, or ordinal level of measurement would be a set of letter grades. So A, B, C, D's, and F's. So you've got a list of students, and the data set consists of their letter grades. Well, they can be arranged in some order. There's obviously some order to this. You can arrange it alphabetically, A, B, C, D, F. So there's some order that you could use to find the possible data values. But the differences between data values are something that you can't determine in this case. If you're using a common grading scale, for example, let's say that A's are 90% and above, and 80 to 89% is a B, and so on and so forth. Well, what's the real difference between an A and a B? If all you have is just the letter grade, what's the real difference? I mean, the A could be a 95, okay, and the B could be an 85, okay. That's entirely possible. So if that's the case, if the A is 95% and the B is 85%, then that means the difference between them is 10%. But what if the B is actually 80%? Well, now the difference between them is 15%. Or what if the A is 90%? Well, now the difference between them is 5%. So what's the real difference between them? You have to have the numerical value to get determined any sort of difference between the data value. Just having the letter grade alone doesn't do it. So the differences cannot be determined from the data alone, and it can be arranged in some order. That makes this ordinal data. Next type we have is interval data. So interval data has three defining characteristics. The first is that it can be arranged in some order. So in that respect, it's like ordinal data. However, for interval data, differences between data values are meaningful. And last, there is no natural zero point. In other words, the natural zero point would be where none of the quantity measured is present. A good example of interval data would be a data set of years. So let's say we have years such as the ones you see here on the screen put into a data set. Okay, that's great. This is what we call interval data. It can be arranged in some order. So we can actually put this in order from lowest to highest. The differences between the data values are very meaningful. I mean, hello, there's a big difference between 1895 and 1970, I guarantee you. One has air conditioning, the other doesn't. One has refrigeration, the other doesn't. One has indoor plumbing. Actually, indoor plumbing was just starting to be introduced in 1895, so you can't really put that in the list. But there's a whole lot of other things you can put in the list, like airplanes, automobiles. Actually, automobiles were just starting to come out in 1895, so you might not put that on the list either. But certainly you wouldn't put airplanes on the list. Okay, the Wright brothers are still a few years away. So there's definitely a big difference between 1895 and 1970. But there's no natural zero point. The year zero is simply a standard year that's been used by Western society, marking the year that Christ was born, and that just comes from the history of Western civilization. So it's not like the year zero means that there's no quantity of year or anything. There's no natural zero point there. These years aren't actually measuring quantities of something from nothing. It's actually the quantity of time that's passed from a given standard, from a given point. And so that point is not where none of the year exists. It's not like there's no time existing in year zero. It's just a point at which we started to set the counter. So that's why years would make a data set at the interval level of measurement. Ratio data is the last of the four, and it has three defining characteristics. The first is that it can be arranged in some order. The differences between the data values are meaningful. So far, we're neck and neck right here, sharing the same bed with interval data. But here's where the roads diverge. With ratio data, there is a natural zero point where none of the quantity measured is present. A good example of ratio data would be a data set of speed measurements. So if you look at your speedometer, okay, you've got all sorts of different measurements that you can take depending upon how fast you're going. It can be arranged in some order, so you can go from highest to lowest or lowest to highest. The differences between the data values are meaningful. There's a big difference between 60 miles an hour and 25 miles an hour. One is for the highway, one is for the residential community. Big difference between the two. And there is a natural zero point. So when you look at zero speed, that's your measurement, zero speed, that means you're not moving. There's no speed to you. You're not in motion at all. So there is a natural zero point, and those three characteristics together make speed measurements a data set of ratio data, or the ratio level of measurement. So just to review, here's a table that gives us some really brief descriptions that helps us to distinguish between the different levels of measurement. So with nominal, you're going to have categories only. With ordinal, you have categories but some order. So remember, nominal data, you couldn't put them in any order. But with ordinal data, you do have some order. With interval level of measurement, you have differences but no natural zero. And with ratio, you have differences but you do have a natural zero. So looking at just these brief descriptions, you could say that nominal and ordinal levels of measurement are describing categorical data, whereas interval and ratio measurements are describing quantitative or numerical data. The difference is, as shown here, nominal data, there's no order to it. Ordinal data, there is an order. Interval data, there's no natural zero point. Ratio data, there is a natural zero point. It's that natural zero point that makes differences between measurements on the ratio level of measurement meaningful. So let's go through a little brief activity to help us learn better what we've just gone through with levels of measurement. So I'm going to give you an example, and you're going to tell me what's the level of measurement for the example. So here we have the first example, the colors. Oh, look at that bright rainbow of chocolate goodness. Colors of M&Ms. Sorry, I just get distracted when I see chocolate. So the colors of M&Ms, level of measurement. I'm going to stare at the picture here for a few seconds while you tell me what level of measurement this is. Okay, I hope you said nominal because that's what this is. Okay, colors of M&Ms, red, yellow, orange, green, blue. These are categories. These are names or labels. There's categorical data, but there's no natural order to them, right? So it's not like, you can say, well, blue has to come first, and then it's red, and then it's orange, and you brown ones, you got to take the last spot. No. You can't list it that way. Well, you could list it that way, but it's not like it's a natural order to the colors, so it's nominal data. Categorical, you can't order. Here's the next example, the depths of kilometers of earthquakes. Again, I'll give you a few seconds. Hope you said ratio data because that's what this is. So you're measuring the depth in kilometers. So you definitely have, you're measuring a distance. So that's not going to be discrete data. It's going to be continuous data. That's quantitative. And the quantitative data, there is a natural zero point. So zero depth means there's no, zero would mean there's no depth. None of the quantity that you're measuring is present in a measurement of zero. So it's not interval, that's ratio. Here's the next example. Years in which U.S. presidents were inaugurated. I'll give you a few seconds. Hope you said interval because that's what this is. Interval level of measurement. So you're looking at years. I mean, that's the dead giveaway right there. You're looking at years. So there is an order to it. It's numerical. It can it's a description of quantitative data, but it's not something that has a natural zero point to it. So that's the tip off there, where years are interval data, interval level of measurement. Here's the next example, a movie rating of 4 out of 5 stars. Okay, here this is an example of ordinal data. So you might be thinking, okay, 4, 5, these are numbers, therefore it's numerical data, therefore I'm going to look at either interval or ratio data. And that's really not what you're looking at with a movie rating. Movie ratings of 4 out of 5 stars, okay? Typically, the way that, at least the way that the statisticians are looking at it, is that you're not rating it with a partial number of stars. You're rating it with a whole number. And the whole numbers are actually categories. So 1 star is one category, 2 stars is another category, 3 stars is another category. So even though you're dealing with numbers, the numbers are being used as a name or a label, and therefore you're going to look at, okay, this is nominal or ordinal. There's definitely an order you can place to it, so it's not nominal, it has to be ordinal level of measurement. Here's the next example, a list of car models subjected to a car crash test. What level of measurement is represented here? Okay, well, I hope you said nominal because that's what this is. So, list of car models. So that's definitely categorical data, but the car models representing different categories, there's no natural order or way to sequence them together, so this represents nominal level of measurement. Blood lead levels of low, medium, and high. What's the level of measurement here? I'll give you a few seconds. Okay, this is an example of ordinal level of measurement. So we have low, medium, and high. So it's definitely categorical. So it's going to be nominal or ordinal. But because there's a natural order to this, okay, low, medium, high. Or you could say high, medium, low. But you wouldn't say medium, high, low, or high, low, medium. No. There is a common sense order to this. And so, therefore, this is an example of ordinal level of measurement. Body temperatures in degrees Fahrenheit of patients in the same hospital. What level of measurement do we have here? I'll give you a few seconds. Okay, here we have an example of interval level of measurement. Body temperatures in degrees Fahrenheit. So it's definitely numerical, and you're definitely measuring quantity of something, and there's a natural way to order it, but there is no natural 0 point with degrees Fahrenheit. That 0 degrees on degrees Fahrenheit isn't measuring 0 temperature. It's just measuring a standard point at which you actually stick something into the temperature scale. So 0 degrees doesn't mean there's no temperature because of the way that the Fahrenheit scale works. So therefore, there is a natural way to order this, but no natural 0 point, and that makes this interval level of measurement. On that note, let's take a look at an example involving two friends, Sam and Steve. They're talking about how cold it is outside, and Sam says the temperature is 2 degrees, an increase from 1 degree yesterday. Steve then remarks, "Well, that means it's twice as warm today as it was yesterday." Now, what's wrong with that statement? There's something wrong with it, so I'm going to give you a few seconds to think about, figure out what's wrong with that statement. It's twice as warm today as it was yesterday. I'll give you a moment. Okay, well, just as we just got done discussing temperature measurements, okay, for degrees Fahrenheit, but also for degrees Celsius. So it doesn't matter what you're talking about here. There's no natural starting point, okay? This is a characteristic of the interval level of measurement. Ratios such as twice are therefore meaningless. And that's the thing. It's like, why would you use a word that describes a ratio when the level of measurement is not ratio level of measurement. That's what's wrong here. It's very inconsistent. Now, with that in mind, what if these same two friends were talking about the temperature in kelvins or rankines inside a supercooled vacuum chamber? Would Steve's statement still have something wrong with it? Why or why not? I'll give you a moment to think of your answer for that. Well, here in this instance, there's nothing wrong with the statement. You could say that 2 degrees is twice the temperature of 1 degree if you're talking about kelvins or rankines. And by the way, if you're talking about kelvins or rankines, you're not going to use the word degree. It's 1 Kelvin, 2 Kelvin, 1 rankine, 2 rankine. These are units of absolute temperature. They're based on 0 having 0 temperature. Okay? So there is a natural 0 point in these temperature scales. Therefore, this is a ratio level of measurement, and so a descriptor that's describing a ratio, such as the word twice, actually has some meaning to it. Well, now I've reached the end of the lecture. Thanks for watching the video. I will see you in the next video or in class, whichever comes first. See you then.